Hi, this is final report for Introduction to Deep Learning project. So in our group, we do automatic scene detection. Our goal is to identify scene changes from millions of frames in a movie. The goal is to help content creators and media providers. For example, they may want to cut a clip at changes. We want to realize this goal using unsupervised learning because existing works are based on supervised learning with expensive human annotators. We explore models without the requirement for labels in the training stage. To be specific, the model we use is variational autoencoder. We hope that this model will be generalizable to new data and is trainable on any movie. So our task is to do architecture search. We first realize the baseline VAE model and try to improve upon it. The dataset we use consists of unique frames from the film Camino Nava. This is a film released in 2016. The images are of 142p resolution. We have around 66,000 frames for training and around 14,000 frames for validation with labels. We do some data augmentation before training. We resize the original image, and also we do random horizontal flip to augment the data.
So here is our approach. We train a beta VAE to learn a latent space for frame representation. This is the general model architecture where we pass an image through an encoder to generate a mean vector and a variance vector. Then we sample from this normal distribution denoted by them to get a latent vector, which is then passed through the decoder to reconstruct the input image. The objective function involves two components. One is the reconstruction loss, which is the L2 distance between the reconstruction and the input. The other one is the KL divergence between the latent vector distribution and standard normal distribution. We use the reparameterization trick to pass gradients through the model. After we train the VAE, we can calculate the distance of latent vectors for adjacent frames to detect scene changes. We pass both the frames through the encoder network to get latent and calculate distance such as KL divergence or L1 or L2 distance. The metrics used to evaluate performance include top K accuracy and average precision. Here are the model architectures that we have explored. The baseline architecture used 5 convolutional layers in the encoder and the decoder, with square inputs of 64 pixels. We first designed a scaled-up version with square inputs of 128 pixels, using one more hidden layer in both the encoder and the decoder, which increased the parameter from 3 million to 14 million. Then we did some structural change by using ResNet 18 architecture in the encoder. Here you see there are more residue connections in the encoder network, and this increased the parameter from 14 million to 18 million.
Here are some samples of reconstructed frames. As we can observe from the results, the two variants both outperform the baseline model in terms of reconstruction abilities, and the ResNet model generate slightly better images than the other. To better visualize the training process in addition to reconstruction, we plot training loss, reconstruction loss, and KL divergence on validation set. As we can see, during training, all three models lead to decreasing total loss and gradually converge to different optimal points. We can also observe that larger betas lead to higher final loss values. This trend is in accordance with the reconstruction loss on the validation set, and is a result of stronger constraint posed on the latent bottleneck as we increase beta. And also, the final KL divergence is smaller with larger betas. Then we visualize the performance change on the three models on the scene change detection task based on 3 different distance measures. Generally speaking, the best performing distance metric is L2 norm, with best accuracies larger than 0.8 for most of the hyperparameter settings. Here are some statistics for our experiments. The best accuracy is achieved by ResNet 18 with L2 distance at beta equals 2. To conclude, we find that L2 performs best in scene change detection task in terms of accuracy. Second, ResNet model performs better than others in that it has more parameters and a residual connection to prevent gradient vanishing. Third, larger betas lead to stronger constraint on the latent bottleneck and result in more compact representations. However, this does not necessarily mean better performance on our task, and there's a trade-off between information preservation and the quality of disentanglement when tuning beta, and both attributes play some role in our task.